Hello, everybody, and welcome to the next lecture, Lecture 7, Part 1. So in this week's lecture, we're going to be discussing representations. In particular, we're going to be talking about simplicity for representations. So we spoke before about Lie algebras and simple Lie algebras, and we gave a definition in terms of ideals, and then we showed that that was equivalent to, or something means semi-simple, a Lie algebra semi-simple, was defined in terms of ideals, and then we showed that if it was semi-simple, we could decompose it into a direct sum of simples. Okay, so this week we're going to look at the same idea, but for representations. Okay, and you can think about it if you want as generalizing the representation of a Lie algebra, the adjoint representation of a Lie algebra on itself. And then, but for the moment, we'll start off directly with the definition of irreducibility for an L module, a representation of a Lie algebra on a vector space. The definition makes sense for any dimensional representation, but here we will focus, throughout the lecture, we'll really be focusing on finite dimensionality. In fact, the whole course really is focusing on finite dimensionality, as any introductory course in Lie algebra should. Okay, so let's look at the definition. So let L be a Lie algebra, let V be an L representation. V is called simple or irreducible if it does not contain any submodules except 0 and V. Okay. So again, here you see a direct generalization or indirect analogy with the definition of simplicity for Lie algebra. And it is called semisimple or completely reducible if it is a direct sum of simple modules. Okay, so again, you see the comparison here with the case of Lie algebras. But here, notice that we're actually defining semisimplicity directly. It turns out to be more useful to find it directly in terms of being a sum of simples, unlike what we did for the special case of Lie algebras. Okay, good. So let's prove the first result. This is a simple result, but extremely important. It sort of gets to the heart of simple modules. And in fact, a lot of the theory of simple Lie algebras, semi-simple Lie algebras. So let L be a Lie algebra and V a finite dimensional L module, L representation. The following conditions are equivalent. So V is a sum of simple modules. 2, the semi-simple, that is a direct sum of simple modules. Okay, so what's the difference here between 1 and 2? 1 is just a sum, so it's just going to be the span of simple submodules. 2 is direct sum, so that means that they have trivial intersection. Their only intersection is 0. Okay, so basically showing it's clear that 2 implies 1, because obviously if it's a direct sum, it's a sum. What's going on here is the equivalence between these two, the non-trivial part is from 1 to 2, which is to say that if you have a sum, you can always take from it a direct sum. And then finally, the equivalence with 3, which is where most of the work is that any submodule has a complement. That is, there exists another submodule. Yes, sorry, maybe perp is not the best to use here. Because this is not orthogonality with respect to any bilinear form. It just means another subspace such that V is equal to V plus V perp, okay? You can always complement it. So if you're looking, for example, in an inner product space, this is obvious. But semi-simplicity, it also holds, and it's equivalent. Okay, so let's look at the proof. 1 implies 2. So let V be equal to the span of some simple submodules S sub I. Sorry, there's a prime missing here, my apologies, typo. So if S is equal to S sub I prime for any distinct, okay, then just remove it and continue until all the summands are distinct. Of course, we can always do that. Everything is finite, so there's no issue. There's nothing to even think about. Now, if we take any two distinct, we take a distinct I and J, and we consider the intersection, S sub I intersection S sub J, then we will have a submodule of S and a submodule of Sj. Okay, the intersection lives inside in S and lives inside in J, And moreover, you should check it if this is not clear to you, this intersection will actually be a submodule of both of them. But S sub I and S sub j are simple and distinct. Okay, therefore, it must be equal to 0. Remember, it's simple, so that means we have two options, that this submodule can either be, submodule of SI, for example, can either be 0 or SI, and the submodule of SJ can either be 0 or SJ. If it was equal to SI or SJ, then you would have an inclusion of one and the other, but that wouldn't make sense, or you would have an equality, basically. You would have the two things were equal to each other. But that's not the case, because we've removed any summands which were equal to each other. We've removed any summands that are equal to each other, therefore they're distinct, therefore we know that the only other option is 0, so which is to say they have 0 intersection. Thus our sum is actually a direct sum. Okay, so it's this trick that one uses again and again with simplicity, is that when you've got a simple object, the only sub-objects inside are going to be 0 or the whole thing. There are only two options. And then that very strong assumption forces a lot of things to happen. It's the argument that you go to again and again and again when you're making arguments with simplicity. Okay, so that's easy. What's even easier, of course, is the other way around, because obviously a direct sum is a sum. So that's trivial. And let's go on to the third part where there's some work to do, which is to say that we can, for any submodule, we can always find a complement. So let W be a submodule of V. W is the thing that we're going to try to find a complement for. Again, we don't mean complement with respect to some inner product or bilinear form or whatever. In this case, it just means vector space complement. But the elements of the vector space complement, it will be simple. That's the important part. Yeah, because it's obviously clear that you can find a vector space complement, but here it should be that this is a submodule, which will automatically. So let V be a submodule and take a decomposition. So we're going from 2 to 3. That means that we're assuming that we have a decomposition of V into a direct sum of simple submodules. Okay, this is what we got here. Now, since V is finite dimensional, which means, of course, that I is finite, by assumption, it is easy to see that we can choose maximal J, okay, such that the summing our submodules over this index set J, okay, just take the direct sum of all of these for this index, it's a subset of the index set, and denote this new space that we have, this new submodule, this new semi-simple submodule, in fact, because it's a direct sum of simples. Then we take the intersection, and then we want the intersection of W with this new subset to be 0. This won't uniquely define it, but there will be a maximum. It is possible to choose a maximum one. So now what do you do? Just start off with S sub 1, see if the intersection with W is trivial or not. If it is, throw it away. If it's trivial, you keep it. If it's not trivial, which is to say it's not, S sub 1 is contained in W, then you throw it away. And then just continue like this. And you can produce a set, subset J of I, which is maximum. Okay. If that's not clear, ask me and I can write it a little bit more clearly. But if you think about it, I think you should be able to see that this is definitely justified. Now, if we take the direct sum of these two, say the sum of these two would be equal to the direct sum, because by assumption the intersection is 0, would live inside in J. No, what we're hoping, what we would like is that this J will actually be the complement that we want. Will certainly be, some obviously would be contained, but it's not clear that this direct sum of W and this proposed complement will actually be an equality. It could be a proper inclusion. If it is an equality, we're done. If it's not an equality, then we need to do, now we need to exclude the possibility that it's not an equality. Okay, so let's assume that we do not have an equality. In that case, there will have to be some simple submodule out of our list. where the k, of course, is not contained, where this k here is not contained in the index at j, such that it's not contained in the span. I've written sum here, but of course it's the same as the direct sum. Okay, think about that. Why? Because if every summand, if every s sub k was actually contained inside here, then the whole space would be contained inside here. So we have inclusion in both directions, which gives an equality. So if we don't have equality, then there will exist some submodule not contained inside here. Now, this s sub k is simple. So now what we're going to do is use the usual trick of talking about intersections. So s sub k intersected with this guy will have to be equal to 0. So here, this is not simple, okay? The sum of these guys are not simple. So we can't really use our usual argument about simplicity here. However, this is simple. And that's enough. We only need one side of the intersection to be simple. So that means that this intersection here have two choices. We can either be the whole thing, which would tell us that sk was contained inside in the direct sum. But of course, that would contradict our assumption, our defining assumption about s sub k. So the only other option left is 0, which means that they have no intersection. Okay. Now what we're going to try to do is we're going to try to use this fact to prove another trivial intersection. This is not quite the trivial intersection that we need in order to prove that s sub j, to prove that this guy here is actually the decomposition, to prove that s sub j is the complement. This is not quite right. We want to change it into this. And that's what these lines here are, this argument. So probably those of you who remember ring theory well enough, you can maybe even see this directly from here to here. But you know what? Let's go through it just for sake of clarity. So let's take an x that lives inside in this intersection. This intersection that we ultimately want to show is equal to 0. Okay, so let's just take an arbitrary element inside here and prove that it's 0. Okay, so we know that we can, of course, write x in the form s. So, oh, sorry, this is the typo. This x here should be a w. These both should be in w to indicate the fact that it lives inside in w. So, okay, so w lives inside in this intersection, which means that w can be written as something in s sub j, and s big S sub k. We write it as s prime. Repeat, s is in sj, the first one. Sj is in s sub k, the second. Okay. Now we can bring over our s, and that gives us a w minus s is equal to s prime. But this side of the equality lives inside an sj by assumption, s sub k, sorry. And now this w lives in w, s lives in sj by assumption up here. So if these two things are equal to each other, that means that they live inside of the intersection of w plus sj intersection sk. But by up here, the trivial intersection that we started with, we know that this is 0. So that means that this element here is actually equal to 0. Or equivalently, it means that w is actually w minus s is equal to 0. W minus s is equal to 0 means w is equal to 0, s. So w is equal to s, and this lives inside in w intersection s. Okay, because it's w is equal to s. They're the same element, but w is in w, s is in s sub j. So that means that this element that we found lives actually inside of the intersection. But that's 0. So that means that w, which unfortunately is typoed as x, isn't w, the element that we started with, actually lives inside in the intersection. Sorry, this element that we chose at the start up here is automatically 0. The element was chosen arbitrarily, which means that every element inside there is 0, which is to say this is equal to 0. Okay, good. So let's just go back one step and just recall what has happened here. We constructed this s sub j. We want to show, let's go back to the slide. We constructed this s sub j, and we want to show that this inclusion is an equality. And then this S sub j will be the complement to W that we're looking for. Okay. What's the first step? Well, we use simplicity to show that we have the intersection between S sub k, some possible other submodule. We want to show that such things don't exist, but to do that, we're going to assume that they do exist and try to get some sort of contradiction. So take some S sub k that doesn't live inside there, then because it doesn't live inside there, this intersection will be 0, and then go through this argument here to show that this implies this new inequality, this new trivial intersection. So now taking this new trivial intersection, we go on to the next page. This trivial intersection, the one we just proved, together with our assumption that S sub j is properly contained in S sub k. Sorry, this is not an assumption. I mean, together with the obvious fact that S sub j is properly contained inside the span. This contradicts our assumption that S sub j is maximum. So this should just say the fact. Together with the fact that S sub j is properly contained in S sub j plus S sub k. This contradicts our assumption that j is maximum. Okay, S sub j was chosen to be the largest, it's not necessarily unique, largest sum over some subset j of these simple summands inside in V, such that the intersection with W is 0. But now we're adding something else in. We're adding something else to j, S sub j, and we're still getting 0 intersection. That means we have a larger set. We have something containing S sub j satisfying the defining condition. This, of course, contradicts the maximality. Hence, we must conclude that no such S sub k exists, and hence that this equality, the inclusion, and sorry, this is going the wrong way. The inclusion is the other way around. This should be an equality, and it concludes that this is an equality, and it gives the required complement. Okay. Good. No, just for the last. No, to move on to the last part, we've now shown that 1 and 2 are equivalent, and we've shown that 2 implies 3. Now what we want to do to show that everything is equivalent, we want to go back. So we find it a little bit easier to show that 3 implies 1. Well, it's actually more or less the same thing. 3 implies 1 or 2, whichever, it's the same. So choose a simple submodule, S sub 1 inside of V. Of course, we can always do this because V decomposes into a direct sum of simples because by assumption it's semisimple. No, this automatically has a complement by 3 by our assumption. You can always choose a complement. And choose a submodule. Now choose a simple submodule inside in V2. If V1 were simple, then we'll be done. If it's not, we can choose a simple submodule inside there. So by assumption, this direct sum of these 2 new simple submodules will have a complement. And then continuing in this way, by finite dimensionality of V, means eventually we have to arrive at a direct sum, like this, which means that we've decomposed our V into a direct sum of simples. And that's it, we're done. We've now just to go back. We've now proved that these 3 conditions are equivalent. First, here is just our definition of semisimplicity. 1 tells us this doesn't matter. We don't need to worry about the intersections. If you have a sum, then you can always take a subset of these sums such that it's a direct sum. And here, more importantly, it says that it's the same as being able to complement a submodule, any submodule. This is a common thing again. It's such an important, whenever you have an important concept, there's usually many different equivalent definitions. That's somehow a measure of the importance of some mathematical concept. The number of different equivalent formulations you can have of the definition. So here, these are just two formulations of it. There are in fact many more, again, demonstrating how fundamental a concept semi-simplicity is. Okay, but anyway, let's go on to, yeah. Now what we'd like to do is we're going to prove, so we've now kind of explored the definition by giving equivalent formulations of the definition of semi-simplicity. Now we'd like to prove a property, a simple but extremely useful property of semi-simple modules, of simple modules, sorry. So we start off just by denoting the space. This should be clear, but why not? We'll just write it down for clarity, the space of L module maps. So this is the maps that go from, they're the k-linear maps from V to itself, which are not only k-linear, but satisfy an additional requirement, which is to say they're L module maps. So whenever you have an element X inside in your Lie algebra L, you can just bring it out. It's linear over L. It's an L module map. All right? And we denote this by, instead of K, just over the field, it should be linear over L, Lie algebra. Now, for a field K, so we're just going to now move a second definition. This is useful in the formulation of the lemma that we're about to prove. You should probably have come across this before in the first algebra courses, but anyway, we'll recall it. So let a field, let K be a field. An associative K division algebra is an associative K algebra, in the sense that we defined many lectures ago, is an associative K algebra such that every non-zero element in your algebra is invertible. Every non-zero element has a right and a left inverse. Okay. These algebras are not assumed to be commutative, but they are assumed, of course, to be associative, which is why we write associative. Okay, so with the definition of a division algebra in hand, let's prove the next lemma. This is called Schur's lemma. As I said, an extremely important result. So let W and V be two simple modules over the algebra L. Any L module map F from V to W is either 0 or an isomorphism. That's very strong. I mean, it shows somehow how strong an assumption simplicity is. And it shows that basically you've just got two options. You've got that it kills everything, or it kills nothing and it's surjective. Okay, these two options should remind you of the fact that in any simple module, you've got only two sub-modules, which is to say 0 and the whole thing. And that's not a coincidence. That's actually where the proof comes from, as we'll see. Second result is that the endomorphisms, the L endomorphisms of the module, the space that we just defined in the previous slide, this is an associative K division algebra in the sense we just defined. So meaning that the elements inside here, the multiplication, of course, is composition as usual. So with respect to the multiplication of composition, we can always invert them. It's associative, the composition, that's clear, composition is always associative. And you can also divide elements every element admits an inverse. And of course, it's an algebra over K. And finally, if L is defined over an algebraically closed field, then we see that this endomorphism ring, requiring that your linear maps from the vector space to itself are actually linear over L, not just over the field. This is incredibly strong and means that the only objects, that the only maps that satisfy this, the only linear maps, are going to be scalar multiples of the identity. So it's somehow coming from the fact that these things are simple. You can't break them apart. There's almost like atoms of the representation theory. And the only way to move them around is by multiplying them by a scalar. They're solid, they're sort of indestructible. Okay, that's sort of the moral. So let's prove this. We start off, we go back to our usual argument when dealing with anything simple. Only sub-objects are 0 and the thing itself. In particular, the kernel of any linear map is going to be a submodule. Okay. That's just by definition. You see the argument here. So if f kills some element v an element of v, then f of x for x in L, it's going to be, it's by assumption, it's linear over x. So we bring the x out, then we've got f of v. Of course, this is 0, x on 0 is 0. Therefore, this new element is again contained inside the kernel, which is to say the kernel is closed under the multiplication of L, which is to say that the kernel is a submodule of V. But there are only two submodules of V, namely 0 and V. Thus, we have two options. Either one, the kernel is equal to V, which means that f is equal to 0. So the kernel kills everything. That is to say, f is the 0 map. Or two, the kernel is equal to 0, which is to say it's injective. It's the definition. So again, you see the same argument repeating itself again and again for simplicity. You take some object you're interested in studying, try to convert it into some submodule, and then use the fact that there are only two of them. And that will give you two options that you need to progress from. Okay, so if it's option one, then we're done. Because remember, we said here, it's either 0 or an isomorphism. So if it's 0, then we're done. We need to show that the second guy here actually gives us that it's an isomorphism. Well, it's given us injectivity, that's one half of it, but we also need to prove surjectivity. So if it's if f is equal to 0, then we're done. That's what we've just said. So 2, so let's assume we're in 2, which is to say we've got injectivity. Now we want to play the same game with the image. Before we showed that the kernel was a submodule, now we want to show that the image is a submodule. But this is clear. If we take some elements, this is in the image. This is in the image of V. We want to show that if we multiply by x, it's going to be, again, contained in the image, which is to say it's going to be equal to f of something, f of v prime for some element. But this v prime is just xv, because we can bring it in. You take it out or you can bring it in, just going in the opposite direction. So of course, this is contained in V, because again, yeah, this is obviously contained in V, it's a module, and then f of V is going to be contained in the image. Hence, the image of V is closed. It's a submodule. But how many submodules do we have of W? Precisely 2. One of them is 0, and one of them is the whole thing. It can't be 0 because f is injective. So assuming that that v was not 0, it can't be 0. Therefore, the image of f has to be the whole thing. So that's to say we've proved, we already had injectivity, now we've concluded surjectivity, therefore we have an isomorphism. That's it. The argument is as simple as that. It's a very, very useful fact, but the proof is actually quite simple. We do have the last piece though. So for the second piece, the third piece, which is to say the fact that the endomorphism is actually a division algebra. So for the special case f of v to v, we see that L is a K subalgebra of the linear endomorphisms. Okay, that's clear. You can add, if you add together two L module maps, it's clearly again an L module map. If you multiply by a scalar, it's clearly again an L module map. And if you compose two of them, then it's clearly an L module map, because you just need to bring it out through two functions this time, but that works. So it's a K subalgebra of this algebra here, defined under closely. It's a K subalgebra. Now, every f that lives inside here, though, it's an automorphism of V. Okay, so remember in the last proof, or the last step, we showed that every map from V to W was either 0 or an isomorphism. Well, if we let V equal to W, then this still, of course, holds. This is just a special case. And in that case, it means that every non-zero map from V to W is actually an automorphism. Okay. Because it's an isomorphism, it's an isomorphism from V to V, which is to say it's an automorphism. That means in particular it's invertible. you can always invert a bijective linear map. Okay. And that means then that every element inside in this subalgebra, every element of this guy here, is going to be invertible on the right or on the left, which is to say it's a K division algebra. That's it. It's as simple as that. Now, the last part, for the last part, we need to assume that our field is algebraically closed. Okay. So if it is algebraically closed, then F will have possibly 0 eigenvalue. Okay. Because the characteristic polynomial will always split, will admit an eigenvalue. So consider the subspace of eigenvectors of this eigenvalue. So it's going to be all the elements V, small v living in big V, such that F of V is equal to lambda V. Now, V sub lambda is an L submodule of V, as we'll now see. It's just a simple argument for the kernel and the image. So take F of X acting on V, bring out your X. F is an L modular map, so we can do this. Now we know that F of V, because V by assumption is contained inside here, we know that it's equal to lambda of V, which is equal to, of course, to bring that out, it's just a scalar, and it's lambda by X of V. So that means that when you act on X of V by F, what do you get? You get lambda by X of V, which is to say this is a lambda eigenvalue of F, which is to say it lives inside here. Okay. So this guy is a submodule, but it's non-zero by assumption. So we have two options. We've shown that it's a submodule, therefore we have two options: 0 or the whole thing. This can't be 0 because there does actually exist an eigenvalue. So there does exist a non-zero element inside here satisfying this because our field is algebraically closed. Hence it can't be 0. Therefore it has to be the other choice, which is to say it has to be everything. And hence our function f must operate on V as a scalar multiple of the identity. So this space of the eigenvalue actually turns out to have to be the entire space. So it just multiplies by a scalar. It just operates multiplication by a scalar identity. Again, the proof is not so difficult once you get used to the trick of turning the problem into a submodule and then using the fact that there were only two modules, 0 and everything. It's just the same trick used again. Once you realize that you need to look at this space, the subspace of eigenvalues. And that's it. So let's just look at that again. It's such an important result. Again, these things, these simple modules are almost like atoms. So when you try to move them around, there's nothing you can really do except multiply by a scalar because they're so rigid. And that's why they're like the building blocks, like the atoms of representations. All right. Upside down. And here we go. Now let's look at something kind of cool. If we recall this very classical result of Frobenius and Peirce, 19th century, they went and looked at the case when the field K was actually the real numbers and looked at finite dimensional real associative division algebras over R. Okay, so real here means that the field that we're considering K is equal to R. And then asked how many of these things exist. So this is the 19th century when people, there were still complex numbers still seemed a little exotic, and then Hamilton had discovered the quaternions. The H here is of course the quaternions. Reals extend to complex, extend to quaternions. The extension to octonions here is omitted because we've assumed associative. And of course these octonions are not associative. And people began to wonder, could there exist any more extensions of R up to some sort of an associative division algebra that people had missed or didn't find? And this proof says no. Basically, you've got just 3, the trivial extension R itself, the complex numbers or H, which is a remarkable result in itself. And the fact that if you actually drop associativity, then the only other thing you get are the octonions. But what we can do now is apply this result to the study of Lie algebra or Lie algebra automorphisms. So if we have a real Lie algebra, Lie algebra defined of the real numbers, and a simple L module, then we know that the L module endomorphisms of this is going to be a division algebra over R. That means we've only got 3 possibilities. So it has to actually be isomorphic to the real numbers, the complex numbers, or the quaternions. Which is quite nice. Okay, and that's where we'll leave this half of the lecture 7, on this nice note. And we'll continue in the next lecture with a few more observations about semisimplicity, complete reducibility, and Weyl's theorem, and something about Casimir operators. And then that's basically this portion of the course finished. And now we're going to move on to the next block, which would be the classification of semisimple Lie algebras, which continues more on this slide. Okay, so thank you for your attention, and we'll talk to you at the next lecture.